Well, while they turn off the music, I'd like to thank the organizers for inviting me in this conference. So I'm the last speaker. I can say it's been amazing. I've seen all your contributions, and I really enjoyed seeing what you are working on in the Human Brain Project. So thanks a lot for this opportunity. So before the music goes off, I'd like to show you where I work, because this is very far from here. So this is the island of Singapore, and I work in this campus, which is design-based, and it's a new one. And it is based next to the airport, so if you happen to go to Singapore, please drop me an email, and we can chat there and meet there. Anyway, so let's go to the talk. Through this conference, I've seen a lot of interactions between machine learning, computer science, and neuroscience or cognitive science, but mostly in one direction: how machine learning can assist neuroscience and explain brain data. So here what I want to convince you is that your work is essential for getting inspirations for us, computer scientists, to build better models, and that cognitive science and neuroscience and these discoveries will inspire us to build these artificial intelligent models that can be better than what we have today. So a bit of introduction. So this presentation I'm going to talk about, it's going to be mainly in the frame of object recognition. So my background is in computer vision, so of course I always work with images and videos. And what is object recognition? So given an image like this one you see here in the slide, you can ask a lot of questions. Like, you can have lots of tasks, like for instance, what is happening, how many people are there, how many bikes, or what are the interactions between persons. But my question is the most basic one, which is like, what's in this image? So what do you see? The answer could be a bike, could be a person, depends, okay? So that's the most basic task. And to put it a bit more in context of machine learning, so what we would like to build is algorithms or models that learn the parameters through examples and then are able to predict the task or what object is in an image that has not been used for learning the parameters. So that's why we divide this in training phase and testing phase. So in training is where the model learns the parameters through the examples, and at testing is when it does the predictions and we can see if it generalizes to new instances. Okay, how we learn the parameters, there are many ways. I'm not going to go into details, but we can discuss this offline later if you want. Let's go inside artificial neural networks. So for me, neuroscience can be very simplified. I know probably you won't agree with me, but when you work at this level of abstraction is good enough. So for me, a neuron does a dot product between the input and the synaptic weights. The input in this case is X, and the synaptic weights is T, and then it integrates this information. So this can be modeled with the Perceptron, which was introduced in the late 50s. And here in this case, you can see that the Perceptron is nothing more than a neural network with only one unit and one layer. So it's very simple. And here the inputs are represented as P. The W are the weights, the parameters that you would learn from examples. And then there is a no linearity. And these weights can be learned using the examples, okay? And this non-linearity can be many different functions. Usually in neuroscience, people use the sigmoid, but you can use, nowadays in artificial neural networks, people use linear rectifiers, or you can use a sine or any other non-linear function. Of course, Perceptron is very simple, and if we think about the brain, we know we have a lot of neurons, so this we can also do with artificial neural networks, so we can add more neurons to one layer, or even stack into layers, okay? And then we can have like a hierarchy of neural networks with a lot of layers and a lot of neurons. Very well. So I told you that each of these neurons or units have some parameters associated that can be learned from examples. So how is this learning done? So when you have only one, this can be thought as a gradient descent. So given your input, you just forward pass through the network, get the responses, then compute the error, and with the derivative, you can redirect the weight such that the prediction will be good, a good one, so what you expect. And this you do with a lot of examples, and you update the weights, and then you can check with other samples if your model can do good predictions or not, okay? And I don't know if I told you that, but this, when you have many layers, it's called back-propagation, and it's like a gradient descent, but layer-based. Very good. So artificial neural networks actually was an abstraction of modeling the neurons, and later on, similar kind of networks were used for building computational models for object recognition. So we know that in the ventral stream, we have different regions that are organized in layers, and they are called V1, V2, V4, and IT. So in V1, the neurons are responsive for edges or oriented lines, and then through this hierarchy, the neurons respond more highly to patterns that get more and more complex, okay? So at IT, for instance, the neurons would be active at pairs of objects or even entire objects. So one of the first discoveries that then later on led to this kind of modeling was by Hubel and Wiesel. So where they were recording the neurons of a cat in V1, and then they were showing to the cat, actually they were showing them or it dots, and they weren't seeing any response at all, and it was a mistake that at some point they showed to the cat an oriented bar, and then the neuron started firing, and voila, the Nobel Prize. If you haven't seen the video on YouTube, I really recommend, because it's really interesting. So with that, they proposed a model of the neurons. So they divided in simple cells and complex cells. So in the simple cells, mainly, they are selective to some oriented bars, and the complex cells merge the information in neighboring positions, okay? So how can we understand this a bit better with a cartoon? So in the simple cell, you would be selective to a particular pattern, and in the complex cell, you don't care where this pattern it appeared. So the cell would fire no matter if it went a bit more to the left or a bit more to the right, it would be invariant to position. It would say this pattern was there in this region. I don't know where, but it was there. So a similar kind of model was used, but now with this hierarchy to model the visual cortex, the primal visual cortex, in which we have like a kind of representation of V1 with simple cells and complex cells that fire to particular locations, and then the receptive fields of the units or the neurons were increasing in the hierarchy. Here I have to say that the parameters of these models were not learned with back-propagation, okay? They were totally random. Well, not totally random, but unsupervised. And here we can see, again, the representation with the simple cells and complex cells. So the simple cells, what is it? Here. The simple cells are the selective ones, and the complex cells, it's called H-max, this particular model. There are other models because they perform the max operation, okay? So they just take the maximum of the responses across neurons that are selective to nearby locations. Very well. So these kind of models were applied also in computer vision and machine learning systems, but they were not as effective as other handcrafted features that people were designing and so on. So they were there were two lines of research, one that was more like the computational neuroscience and another one that was more computer vision. And this was only recently that models that were inspired by these architectures that were brought back again to computer vision systems and many other applications in artificial intelligence. So probably you know the story, but I'm going to recap a little bit. So when this happened, actually there is a particular point in time. A group from Toronto participated in a challenge that was considered very difficult to have very high performance for object recognition. So the challenge, I think, at least the data set is available, but the challenge is not on anymore as it was at that time. So they use a deep neural network trained with back-propagation for object recognition, and they won the challenge, but by a big margin compared to the previous methods. So that's when people started looking back at neural networks and see if they had potential for many other applications in computer science. So there are many reasons why this was possible at that time and not was possible before. Some of them is because there was a lot of data available. These models need to learn a lot of parameters, so they tend to just feed the data for training and not able to generalize, but in this case, the amount of data was enough. And then, of course, the computational resources, because as you can imagine, there are a lot of convolutions, multiplications, and this is very computationally expensive. So you need GPUs for being able to train these models. And as I said, they really got really good results, so everybody was looking at it at the beginning, not believing it, but as we all know, even now neuroscientists use them, so probably they do work very well. So as I told you, these models now are being used for explaining brain regions, not as exact models of the brain, but to try to understand regions of the brain and what they are doing, so the functionality. Okay, so is it really modeling human vision perception? Of course, we can use them to understand the brain, but we don't really know if these models are really a good model to say that the brain is like that or not. Okay, and one of the first observations that one can do is that these models capture the image only in high resolution, and it's not the case with humans. So we know that there is less visual acuity in eccentricity. So visual acuity descends here. 0 degrees is the fixation point. Eccentricity is the distance to the fixation point. And visual acuity is how well you can see the object. And this decreases with eccentricity. So this mainly means that you perceive the image or the world in high resolution at the fixation point and in lower resolution at the periphery. This is one difference that it's quite evident. You don't need to think a lot about it, even though we don't realize probably that we see blurry at the periphery until we think about it. And another observation is that so when we do object recognition, we can immediately detect the objects even though they are presented at different scales and at different positions, even though we have seen this object, this particular object, only at one scale and one position. So how is this possible? At pixel level, the images are completely different. So these neural networks really need to see all these variations at training to be able to generalize across different scales and different positions. So this is a question that we can think about and then try to think if we can come up with a better model that can capture this property. So this is, leads me to a model that we introduced, and this is joint work with my collaborators at MIT. Francis is a graduate student, that's why he was more the hands-on, but we all collaborated, of course. So the eccentricity model, where does it come from? So what's the eccentricity? As I told you, is the distance from the fixation point. If you look here, to imagine that the object is here, so this would be the eccentricity that the object it is, okay? And then, so if an object distance decreases and its scale increases, its eccentricity increases. What does this mean? Okay. So let me show you this graph. And I'm going to do it with a little example. So here, this is eccentricity. This is the fixation point. And this here represents scale, okay? Here I only have x, but we could have y as well, like the plane of the image. But for simplicity, I only show you one dimension. So if we have an object that is small and close to the fixation point, imagine that you get your hand, put it in front of you. You see a small hand close to the fixation point if you look at the center. And then, following this line, how we obtain that? So we have the hand here. We shift it towards us. So it becomes bigger. In the projection to the retina, of course, the hand is the same. And farther away from the fixation point, if I keep looking to the center, okay? Or forward. So this is this representation here. So if we now think that we can recognize objects at different distances without changing the position, then how can we capture this with a model? So this would give us like an inverted pyramid like this, because of course the visual field is symmetric, so we want to be able to recognize in both sides of the field. And it's truncated here, the pyramid, because we cannot go to infinite towards us, okay? There is some limitation there. And so how can we model this with a CNN? Of course, now we have these very powerful models, so we want to leverage them, but we also want to incorporate these properties and see if we can get what we desire, which is invariance to scale and position. So how can we get them? So again, this is the inverted pyramid. So we can have units or neurons that sample at different scales, at different positions. So here, what we have is that this is the smaller scales. So the receptive fields at the smaller scales will be smaller. So they capture the image with high resolution. And here at the larger scale, they are larger and they capture the image at smaller resolution, okay? And one of the important things in this particular model is that the number of units at each scale is constant, is the same, because we want invariance to scale. So the same receptive field here would be there, but at different resolutions, okay? And at the image level, this is how you would get this. So if you have an image, and imagine that you feed this to the model, so what the model sees is different crops of the image. So this would be the higher resolution, which is this crop here, and the larger one is the larger scale, and the lower resolution here. So now imagine that if you would have a very small 8 here, you would see this, but there. And now you can intuitively see that this would be scale invariant, because the information is somewhere in some of these crops, so we just need to gather it. And the pooling operation that I was telling you before will help us to get this invariance. Here the architecture, so it's mainly a CNN architecture, but now we not only share weights across position as usually, but we also share across scale. So it's like having a channel per scale, okay, a scale channel. And then we can pull across positions, but we can also pull across scales. And of course, since these networks can be hierarchical, we can also build a hierarchical neural network with this scale property, or these scale channels, okay? Just to emphasize a bit that the pooling over scales is exactly the same as in position, but here we have different scale channels. And then we would, for instance, do a max operation between activations at the same neuron at different scales. So the neuron that responds to the same function at different scales. okay? So it doesn't matter in which scale it appears, that if it's there, it will be activated. Of course, we don't know how to pull, like, should we merge all the information across scales at the beginning of the network, at the end of the network, incrementally? Luckily, this is a model, so we can try all. So we compare a couple of strategies. Early model means that we pull across scales at the first layer. Incremental, this 6 means that we use six crops, so 6 different scales. Incremental means that we do it incrementally across layers. So at the last layer, there will be invariance, but at the previous layers, only across several scales. Okay? And then it comes another question. So we know we have data. This is from macaques. That if we compare the eccentricity of, let's say, of the receptive field in degrees with the receptive field size in the macaque brain, at the V4 layer, there are not huge receptive fields. But in the model I presented, this would be filled, right? So we can try to also incorporate that. And the question comes, we should get rid of these guys here. How do we do that? We just propose a chevron model. Chevron because it has the chevron shape. And this is just an implementation detail. You can do it with better ways. If you know how, you can tell me. And then we can measure the receptive fields of our units in the artificial neural network across different layers, and then have like a similar size across the layers as we saw before. Okay? And we, again, since it's a model, we can try different sizes and different ways of doing this chevron model. And for learning the parameters, we use deep learning. Why we use deep learning? Mainly because of the first reason, because it's very powerful. It can make very good predictions. Interestingly, these kind of models can also find very good correlations with activations in the IT and other regions of the brain. So that might be a good reason as well, arguably. And then we also use, as I presented before, this comes from neuroscience, so similar to simple and complex cells, which are like the parameters, the filters, and the pooling operations. And interestingly, at the first layer, if you check the filters, they are Gabor-like, which is the same in the V1 of macaque or human brain, which is also interesting. But anyway, you can find Gabors with any technique. You do BCA and you also find Gabors, so anyway. So here are some results. So we, of course, measured invariance because that was our first hypothesis. We wanted to work on these invariance properties. So we performed several experiments. Here I'm only going to show 2 of them as scale invariance at the fovea, which means at the center, and translation invariance with different sizes of the stimuli. For scale invariance, we want to enforce that we have around 2 octaves of scale invariance. Luckily, we can modify this with our chevron model. So if now you come with your experiments and you tell me, no, it's like a broader range, so I can incorporate this to my model. And maybe for my artificial intelligence application, I need like more range, so I can also modify it. And the setup is the following. So we use MNIST. I will show you how MNIST look like. Okay, it looks like this. So they are hand-digit numbers, handwritten digit numbers. And so there is a data set. It's a very simple data set. Why we use this one? Because it's very easy to manipulate. So we can create digits that are larger, that are embedded in larger images, and we can shift them, and then we know if the representation is invariant to what, because we generate it synthetically. Whereas in natural images, this is much more difficult to control. Okay, and we do several comparisons. Here, flat means that doesn't have scale, so it's like just a CNN. and the eccentricity model. Okay. So here, what I'm interested, so you should focus in the blue line and in the yellow line. These are the two most important. So this is relative scale to the one used at training. So 0 is the same scale used at training, and then this is larger, and this is smaller in octaves, and here is accuracy at the test set, okay? So what we can see is all the models perform really well when the size of the digits are the same as training, of course. But when we change the size, then the CNN is not able to generalize to the different sizes, whereas the eccentricity model is able to generalize, since we use chevron of 2, to another size. If we would increase this chevron parameter, then it would be invariant across many more sizes. Okay. So now we can perform another experiment, which is like translation invariance. We again use MNIST embedded in a larger image, and we shift around this image the digits. And for training, we always use the digits at the center, and then at testing, we shift them around along the horizontal line, and we evaluate the accuracy performance. Okay, so here are the results. This is for the eccentricity model. So here, what we have is results for different digit size. Okay, the model have been trained on this particular size. We are not checking size here, only position. And what we can see is that the larger the digits are, the more invariant they are in position, and the smaller they are, the less. And this kind of matches the inverted pyramid. So the range of invariance, it's the same as the range in its particular scale in the pyramid, roughly. And then here we can see the results with the CNN. So the CNNs are inherently position invariant. So here what we can say is that we have a similar trend. So the digits are also invariant in position, but remember that they are not invariant in scale. This particular one, for whatever reason, we weren't able to train it. So that's why it gives chance, but doesn't mean that we couldn't. We just couldn't do it. But maybe you find better parameters. So to summarize this, the eccentricity model prioritizes actually scale over shift, and we can change it with the chevron parameter. The translation invariance depends on the spatial pooling range in the inverted pyramid. And in our case, we saw that incremental pooling of scales gives better scale invariance. So here, intuitively, if you pull everything at the beginning, you lose a lot of information already at the first layer, which is only detecting edges. So this might be too crude and eliminates too much information. So another experiment that we could do is crowding. So how these models behave in clutter. And I'm going to explain what crowding it is, just for those that might not know. So when we want to recognize an object, a target object, so for instance, A is your target object, and you are fixating here, if you add some flankers that are not occluding the object, so they are not occluders, they are flankers, the information might be merged, and as a human, we cannot detect the target object. Okay? This is a very well-known phenomenon. It's been studied quite a lot in cognitive science and psychology literature, and some of the findings or explanation of crowding, it's summarized in this Bohm's law, that what it says is that for being able to recognize the target object, this A here, the flankers, the X's, should be spaced at least half of the eccentricity of the target object. So this is the eccentricity, the distance at which the target object is. So these guys here should be at least apart half of this eccentricity. Otherwise, there will be crowding, so you won't be able to recognize this A. Okay? So this is joint work with Anna and Tommaso. Anna is a student at ETH, but she was visiting at MIT. So a bit more of background. So we can have a lot of sources of variation in images. Here you can see some of them: viewpoint variation, illumination, conditions variation, scale variation, deformations, occlusions, intraclass variation. Here, what we are more interested in is in this background clutter. Why? Because we claim that crowding is a special case of clutter. So here again, if you fixate your gaze here, I don't know if it will work because, of course, this depends on the distance you are, because eccentricity is measured, is the projection of the image to your retina. So if you try to recognize this boy here, you can see it without any problem. But in this other side, it's exactly at the same distance to the fixation point. But since there are these flankers here, you cannot see this little boy. Okay? But the position is exactly the same. And it's not occluded. I don't know if it works from your distance, but at the distance it should be, it works. So what we want to see is that if neural networks have also these similar effects to clutter. So how clutter affects object recognition in these artificial neural networks. And of course, since we have our eccentricity model, we also want to check how it affects the eccentricity model. Okay, so just a small recap. Convolutional neural networks are hierarchical neural networks based on convolutions, and they see the whole image in high resolution. And the eccentricity-dependent model, it depends on eccentricity and perceived with high resolution at the center and lower resolution at the periphery. Here we have another cartoon of how it looks like. This is how the model perceives the image. And these are the several crops that the model extracts from the image. And here again we use MNIS, but here for crowding we use recognition performance to assess if there is crowding or not. Since these models are trained in a supervised fashion, what we use is even digits as our targets and odd digits as our flankers, and we also used other kind of characters to see the effect on different shapes, but I won't report this here. And so the first setup is we can train our models with the clutter and see if they can generalize at test time. And then we can test without clutter, with the same clutter configuration, or with different clutter configurations, and see what happens. And of course, we'll change in eccentricity, so this will be 0 for the image, and this is shifted towards the periphery, okay? Increases eccentricity. So here we report some results. What we see is that this is the distance at which the flankers are from the target. So this is the configuration used at training. So we can see that both models perform really well at all eccentricities, and there is no problem. So the model is able to learn that the flankers don't matter, or maybe they matter, but it's fine. But when we test with the target in isolation, then there is a drop in performance. It's interesting to see that there is more drop in performance at CNN than with eccentricity model, but at this point, I cannot really tell you why. And again, if we use another configuration, like more spacing, the drop is there as well, okay? So here what we can conclude, or what this suggests, is that we can train with clutter, and then would be not a problem. But then we would need to train with all possible configurations of clutters, and this doesn't sound, for instance, very plausible for humans. So I would like also my models to be robust to this clutter. And I would need too much data. So also this would require a lot of time and a lot of computational resources. So I suggest another configuration. So let's try to train without the clutter, just the object in isolation, and then test with clutter and see what happens. Let's see if it's able to generalize when you embed it with clutter. So here's the setup. At train time, you only have the target object, and at test time, you also add the flankers or the clutter. And again, we test in different eccentricities. And here what we find is that, of course, the different eccentricities, this is eccentricity, this is accuracy for both graphs. We are able to recognize the object at all different positions. But when we add the clutter or the flankers, these X's, one on the right and one on the left, what we see is that at the CNN, it really suffers from crowding, as psychologists would say, so it impairs recognition. Well, at the eccentricity model, if it's at the center, the object, it's a bit lower, but it's still okay. So it's actually pretty reasonable. And of course, the accuracy decreases with eccentricity. So this sounds promising, and we can maybe try to make it more challenging for the models and see what happens. So again, at training, we use the object in isolation, and at test, we embed the numbers to scenes or like normal images. This is actually from Places dataset from MIT. So we consider this to be a complex clutter. And again, we shift them, we shift the objects, we change its position. So what we see is that the CNNs fail miserably. They just merge all the information and they cannot extract the pattern, which could not be the case, could work, because these networks have been trained to recognize this particular pattern, which are numbers, and the background doesn't have numbers, so why should it be confused, right? It should be selective, but they are not too selective, apparently. And again, we see that the eccentricity model, even though it's a bit lower than without the clutter, when the object is centered, it does reasonably well. So here is some conclusions of this work. So we could train with clutter, but this would be too expensive, and we should find all the possible configurations that we could have at test time. So what we could do is just train without the clutter. So we would need less examples at training time, so low sample complexity. And then use the eccentricity model, and we could have a separate mechanism, or maybe integrated ideally, that could fixate this model and center to the object. Okay, so use a kind of foveated or fixated kind of a gaze mechanism. Okay, with the advantage that if we are able to center this model in top of the object, we also have scale invariance. So again, even lower sample complexity, which is always desirable. And okay, so we have some code if you are interested online, and more details in the papers. And I don't know if I have time. Okay, maybe 2 minutes more for the last part. So this is a bit more farther, is even farther from neuroscience than the work before, but it's still inspired from the human mechanisms of the visual system. So we all use now deep neural networks and are very happy because they have very good predictive power, but they are very easily fooled. So if we have these images here, and we had just a little bit of noise, that when we sum this up, the images look the same to us. These models, whereas before they could recognize these objects here, now with this noise, they can no longer recognize them. We don't know why this happens. Well, we'll know a little bit, but this can become a problem, especially if we want to bring these models to the market, because then they are very easily hacked. So here you can see, so these are just the names of the algorithms to generate these perturbations. And here is how the perturbations look like. This is the image, which, as the other speakers, look better in my computer. But anyway, you get the idea. And then here you can see on top of each other. So this noise has been increased. It's not the minimum one, so you can see that where it is in the image. Sorry. And this is joint work with Luo, Javier, Tommaso, and Kitsao. So one of the hypotheses that people have why this happened is because these deep neural networks, so they are function approximators. This is the image and this is the noise. They behave like linear functions. So even though this noise is very small, when this is a high-dimensional space, so when sum them up, it can really affect the final result. Okay, so this is one hypothesis with some proofs, of course. But here what we show is that if this was the case, it doesn't matter which kind of noise it is, right? Because it just sums up and that's it. But if instead of adding this particular noise, you just add random noise and even increase its norm, it doesn't really affect accuracy that much. Okay, maybe if you add, this is definitely occlusion. It's not anymore this kind of noise. And if you generate noise, so this is one model that people call AlexNet because it was designed by a guy named Alex. So if you generate the noise for this particular network and for the particular images, then it really breaks the performance. But if you generate the noise for other networks and then try to classify it with this AlexNet, then of course the accuracy is impaired, but it's not that much. So why is that? So the imperceptible noise would be at this point here. This is already perceptible. Okay? So here is an experiment we do. So we generate this perturbation, the minimum one that breaks performance, and then we, instead of summing to all the image, we just add it on top of the object. So we have a notation for bounding boxes, so we know where the objects are. So we just paste the object, we just paste the noise that lies on top of the object. And here we can see that it almost affects the same. But if we paste it only on the background and the object is free of noise, then it doesn't affect that much. Which again, this kind of doesn't align with the linear hypothesis because background usually is larger than the object in most of the images. Well, not in most of the images, but in some images, okay? So here is a new hypothesis. So the CNNs are not linear in general, but are locally linear because they respond to the objects. They are being trained for recognizing particular objects. So they behave as linear when they detect the patterns of the particular objects that they have been trained on. And where else it behaves, we don't know. Maybe non-linear, but we cannot claim how they behave, okay? And then we also know that these neural networks are robust to changes in scale and position of the objects, not because they are invariant representations, but because they have seen many objects at different scales and positions. So at the prediction level, they are robust to these changes, but not before. So here what we claim is that these networks are robust to such changes, but not to changes in perturbation. So if suddenly you change the scale of the image and the perturbation is already there, so you also change the scale of the perturbation, then it shouldn't break performance anymore. That's the hypothesis. So, and here comes the inspiration from a human visual system. It's a very simple one. So we know that we don't see everything in full resolution, but we fixate and then integrate the information. So the only thing we take from that is that we apply some kind of foveated mechanism. So here is the image, and here is a very artificial foveation, so it's not natural, but we just like kind of zoom in, we see it larger, so it's a crop. And this is the first set, where the noise is applied to here, okay? To this image. And in here, we do the same, but when only with the cropped objects. So we generate this noise for the cropped objects, and then maybe we shift a little bit the image by 1 pixel or 2. And here are the results. So these are the different models. So I'm just going to report for this one. So this is the accuracy that we get without the perturbations, quite high. It's a bit lower, I think, than the original paper, because we don't do all the tricks of augmenting data and so on. We are not interested in that. And this is for only the object, so the cropped object, and without the perturbation. Here, without perturbation, we can see that the accuracy almost dropped to 0. So the images are not anymore recognized by the model. But then when we do this crop, we recover the accuracy. And again, we could do this automatically with some saliency detection mechanism, and we also recover the accuracy. It's a bit lower because there is a loss in precision, of course, in the position of the object. And here, when we do it with the whole object, we can see a similar behavior. So this is shifting only 1 pixel. So by only 1 pixel, we already recovered quite a lot. Or we embed back the image to the cropped object to the original image, which shouldn't affect, because we have seen that the noise only affects on top of the object, but still, we can recover quite a lot the information. Okay, so with this, my last conclusion. So for the adversarial example SPAR, so these are consequences of local linearity and not totally linear. That's our claim. And that the CNNs are robust to this scale and positions, but not to changes in perturbations, and that the fovation-like mechanisms can alleviate these adversarial examples or the effect of the perturbations. So here the final conclusion: if we have a system that somehow can position an eccentricity model on top of the object, and we integrate the information with different gases, this would give us robustness to perturbations, and this would give us robustness also to, or invariance to scale and position through the fixations. And this concludes my talk here. And as an overall summary, in computer science, we have a lot of need of neuroscience inspiration and cognitive science inspiration. So I think there is here an opportunity not only to go from computer science to neuroscience, but to go back and close the loop. So thank you very much.